Welcome to myprojectbazaar.com. Here we discuss about an active soft switch phase shifter full bridge DC to DC converter, analyzing, modeling, design and implementation. Full bridge DC to DC converters are conventional choice for medium and high power applications. Isolation transformers providing high voltage gains apart from providing isolation. Switching at high frequency provides better power densities, but overall system efficiency reduces because of increasing switching losses. Soft switch full bridge converters such as ZVS PWM full bridge converters addresses these issues. Salient features of the circuits proposed in these papers are wide range of ZVS, complexities in implementation, higher conduction loss during freewheeling intervals. Some of the auxiliary switches are not soft switched. A new active soft switched circuit for non-isolated and isolated converters is proposed. The novelty of these circuits lies in achieving soft switching for both main auxiliary switches and gating the switches to auxiliary switches or gate referred. Proposed active switch ZVS PWM full bridge converter had two identical auxiliary cells connected conventional full bridge. The full bridge zero voltage switches converter is the most widely used soft switch circuit in high power applications. This constant frequency converter employs phase shift control and features ZVS of the primary switches with relatively small circuitry energy. However, full ZVS operations can only be achieved with a limited load and input voltage range unless a relatively large induction is providing in series with the primary winding of the transmitter, either by an increased leakage inductance of the transformer and or by an additional external inductor. This increased inductance has a determinal effect on the performance of the converter since it causes an increasing loss of the duty cycle on the secondary side as well as severe loss of voltage ringing around the secondary side outside rectifiers due to the resonance about in between the inductance and the junction capacitance of the rectifier. In this paper, a full bridge ZVS converter with adaptive energy storage that offers ZVS of the primary switches over a wide range of load with great reduction no load circuitry energy and with significantly reduction secondary side duty cycle loss of introduced. Now I am going to explain the flow diagram of our project. In the first stage of our flow, we give the irregular or unregulated DC input to our circuit of full bridge converter circuits which are designed by using CMOS designs. To give the controlling signals to each and every switches in the CMOS circuitry in full bridge converter circuit, we provide a feedback signal to our control circuit which are made by using CMOS technology. The feedback signals was first fed to the error amplifier, which will give the amplified signals of millivolts to certain voltage ranges, and this voltages was given to comparator. This comparator stage which compares the reference signals and the error signals and provides the pulse generator outputs from comparator output of our desired error signal. Then this pulses was given to the since by using the full bridge controlling circuits of DC to DC converter, we get the clear result of regulated DC supplies at the output of load regulations. Here we using the buck converters which reduces the unwanted and regulated power supplies from our input unregulated DC supply. At the load side, we get the regulated DC supply which are made at any differences of input variations according to our controlling pulses which are provided by using the feedback signal. Then this was given feedback to the CMOS switching circuit to control the overall switching devices of that full bridge converter circuit. Then according to the switching devices we get the regulator supply at the load side. Now I am going to explain the running procedure of our project. In the first stage, we use the unregulated DC supplies at the internal structure. By using the DC voltage input block, then from the DC input block, we fed the DC supplies to our full bridge DC to DC CMOS converter circuit. Then, to pass the regulated DC supply at the load stage, we provide a coupling capacitor and uncoupler inductors along with the load resistor. From the load side, we extract the feedback signal from the error which are generated across the load, and this was fed to error signal to error amplifier circuitry. In this error amplifier circuitry, it amplifies the error signals and gives this error amplified signal to comparator circuit. The comparator circuit will check the comparison between error signal amplified and the reference signal which are gives the as the inputs of input secondary to comparator. Then according to the comparison results of both the reference signals and error signals, we generated a pulse which is fed to the gate terminal of our full bridge DC to DC converter circuit. From that DC to DC converter circuit, it checks the switching activations of each and every triggering sections of pulse widths according to the timings and generated the switching activities, and finally it provides the regulated power supplies to load side. The benefits of our circuitry is it will regulate the DC supply even if there was unregulated and different voltage sources which are provided at the internal circuit. Even though we can use the dynamic voltage load resistor at the load side, it will generate the constant DC output at the load side. Now just click the run buttons to run our circuitry. Finally, we can view the signals of inputs and output terminals and the references on the pulse which are need to triggering input for full bridge rectifiers or can be viewed in the scope designs. Thus we regulate the internal DC supplies for of unregulated DC input, and finally we get the regulated DC output at the load side. Thus we run our project. Thank you.